Hi, welcome to another lecture in the series of engineering chemistry. So we are still in part one, and this is lecture five. So we want to look at oxidation and reduction in the lecture five. So we're gonna look at the definitions and the types of the reactions that we can see oxidation and reduction occurring. So oxidation occurs when an atom or ion loses electrons. For example, you see sodium uh, loses an electron and then sodium is oxidized. So reduction occurs when an atom or ion gains electron. So when it gains electron, it's called reduction. So for example, you can see chlorine gains an electron to become chloride ion, and therefore chlorine is reduced. So please take note of that. When it loses an electron, they are oxidized. When they gain electron, they are said to be reduced. So oxidation and reduction. So when you bring the two of them together, we call them redox or redox reaction. So losing electron is oxidation, as we said in the previous slide, and the substance that loses electron is called reducing agent. Okay, so gained electrons is reduction. And the substance that gains electron is called the oxidizing agent. So for example, from the previous slide, we see that sodium loses an electron. Therefore, sodium is a reducing agent. Again, we see chlorine gains an electron. Therefore, chlorine is an oxidizing agent. So I take that again. From our previous slide, you see that sodium is oxidized. That is, sodium loses an electron. Therefore, it is called a reducing agent. In our previous slide also, we see chlorine is reduced to the chloride ion, and then that means that it gains an electron. That means chlorine is oxidizing agent. Please take note of that so that we don't confuse these definitions. So, oxidation and redox reaction. One cannot occur without the other in a reaction. The two of them have to go together, and that's why we call them redox reaction. So when you have a substance losing an electron, definitely you're going to have another substance gaining the electron that has been lost. So oxidation and reduction, let's consider some examples. You can see from this reaction, you can see magnesium and sulfur reacting together. So in this case, you see the magnesium is moving from 0 to +2. That means it's losing 2 electrons. You can also see sulfur is gaining the 2 electron that has been lost by magnesium to become S2 minus. So it's gaining an electron. So you can see that both oxidation and reduction are occurring together in the same reaction. So magnesium is oxidized, it loses 2 electrons to become Mg2 plus. That means magnesium is going to be the reducing agent because it's the one losing electron. So sulfur is reduced, that is, it gains an electron, 2 electrons to become S2 minus ion. And therefore, sulfur is going to be the oxidizing agent. So now we can also look at oxidation and reduction from this angle. An increase in oxidation number is referred to an oxidation. Then, and decrease in oxidation number is referred to as reduction. Let's see the same example that we've treated. Sodium is moving from 0 to +1. That is going to be an oxidation from this definition. You can see chlorine is moving from 0 to -1. That is reduction. So from this perspective, we're going to say this is a reduction. Chlorine is being reduced from 0 to -1. So oxidation number. Oxidation number is a positive or negative number assigned to an atom to indicate its degree of oxidation of or reduction. So we must have been seeing those numbers when you write Na plus or Cl minus. So those plus and negative numbers, they're the one that we refer to as oxidation number. So oxidation number can be used to determine which atom or ion or element has been oxidized or reduced. So by the time you write the oxidation numbers out, you see what has happened. Is this atom gaining electron or losing electron? So from there, you will know, is it oxidation or is it reduction? So these numbers can assist in balancing redox chemical reaction. So by the time we get to redox chemical reaction, you see how we're going to use this number to balance the equation. So oxidation number of some elements in the periodic table, I'm very sure that we are familiar with some of them. So if you look at group 1, it's going to be +1, +1, +1, +1 because they are group 1. So if you look at group 2, it's going to be +2, +2, +2, most especially because they are group 2. So if you look at this, you see that they are +3, +3, +3, mostly because they are group 3, and so on and so forth. You can see group 7 is having -1, -1, -1, -1. Then you can see that in between we have the transition elements, and we already know that the transition elements, they have variable more than one oxidation state. So how do we determine the oxidation number? So there are some rules that we need to follow when determining the oxidation number. So elements in their natural elemental form have an oxidation number of 0. For example, iron, it's in elemental form. It has not combined with anything. It's just an ion. So it's going to be 0. For oxygen also, it's in its elemental state. So it also has a 0 charge. They have no charge. Now, the oxidation number of monoatomic ion, by the time you start talking about ion, then you start talking about oxidation number, is the same as its charge. For example, when sodium is being charged, when it is Na+, the plus on top of it is the oxidation number. So we can literally say that the oxidation number of sodium is +1. So there are some other rules. Non-metals in a compound tend to have negative oxidation number. If you check the periodic table, the atoms that do have a negative oxidation, they tend to be towards the non-metal side. So for example, oxygen is a non-metal and it has oxidation number of -2. But in an exception, in peroxide ion, it has an oxidation number of -1. So those are some of the exceptions that we have to this rule. For example, we also have hydrogen. Hydrogen is also a non-metal, and hydrogen is have the two types of oxidation number. It can be -1 when it is bonded to a metal, and it can be +1 when it is bonded to a non-metal. So for example, this is HCl. Cl, that is chlorine, it's a non-metal. So when hydrogen is bonded with a non-metal, it is +1. So as you can see, hydrogen is giving the +1 electron to chlorine to balance or to form a bond in between them. Then you can see this is sodium is a metal, and sodium is already +1. So you can't have another +1 coming to join with +1. So anything that is coming to sodium has to be negative. So that's why hydrogen is -1 when it's being bonded to metal. So some other rules. So we have fluorine also has an oxidation of -1. There are some exceptions also. So for example, all halogens, they're expected to have oxidation number of -1, and they can have positive oxidation number as well. However, most notably in the polyatomic oxyanions. Example, if you see these two examples that we have here, you can see that the halogen is having +1, The halogen in this compound is also having +5. So by the time you work it out, you can see that, it's actually, they are carrying a positive oxidation number. So the sum of oxidation numbers in a neutral compound is 0. So when you have a compound, for example, sodium chloride, the oxidation number of the total oxidation number is, when you sum them together, they have to give you 0. Okay, so the sum of oxidation number in polyatomic ion is the charge on the ion. So for example, if you see the P043 minus, so the oxidation number of this polyatomic ion is -3 because of the charge on top of it. So it's -3. This is also going to be -2. So remember, this is the difference between them. When they are a neutral compound, is 0. But when they are charged compound, then the oxidation number is going to be the charge that is on them. So you do some learning check. So we have to determine the unknown oxidation number of the underlying atoms in the following examples. So chlorine is being underlined here. We don't know the oxidation number, so we want to determine it. Then also here, nitrogen is being underlined. Let's check. So we already know that oxygen has -2 oxidation number. And how many oxygen do we have? We have 4 oxygen. So it's going to be chlorine plus 4 times -2. So if you work it out, you're going to get, and the total is -1. Remember, the charge is -1. That's it, it's equals to -1. So if you work it out, at the end, you're going to get +7. All right, if you also see this example, we already know that sodium is +1. So we know sodium. Then we know that oxygen is -2. That's -2 times 2 because we're having 2 oxygen there. So we have the nitrogen that we are looking for. So if you work it out, and everything is going to be 0. Why? Because this is a neutral compound. It's a compound, so everything is going to be equal to 0. So if you calculate it, then you see that the nitrogen for this compound is +3. Then we have other examples that you can do as we've done to the previous 2 examples. You can see here, we already know chlorine, so you can work it out, and everything is going to be 0. For this one, everything is going to be equals to -2. Then you can work P. So we have types of redox reaction. So most metal react with non-metal to give an ionic compound. We've already treated combination reaction or synthetic reaction in our previous lecture, but we want to look at, when it comes to redox reaction, we're interested in what is reduced, what is oxidized, the oxidation number. So for example, you can see that sodium is 0 oxidation number. Chlorine is also 0. Why? Because they are in their neutral state. But when they combine, you can see that sodium is now +1 and chlorine is -1. So in other words, sodium increases, that is oxidation, and chlorine decreases from 0 to -1, that's reduction. So we have some other examples of non-metals. For example, if you see phosphorus is reacting with chlorine, and you can see that phosphorus is 0 elemental state, and chlorine is also 0 elemental state. So by the time they combine together, you can see that their oxidation number now begin to vary, changes. Chlorine, you can see that phosphorus moves from 0 to +3, and chlorine moves from 0 to -1. Then you can also see the examples here below. So for decomposition reaction, you can see that silver is also moving from +1 to 0. And oxygen is -2, so it's moving from -2 to 0. So silver is being reduced because it's moving downward. It's being reduced, and oxygen is being oxidized because it's moving from -2 to 0. That's increasing. That's it. And a typical example of decomposition reaction. Another one is oxygenation reaction. So oxygen is a powerful oxidizing agent and it combines with most elements forming oxide. So if you see lithium, example, lithium is combining with oxygen here to give you lithium oxide. And you can see the oxidation being changed as they moved. So lithium is moving from 0 to +1. That is oxidation. It's increasing. And oxygen is moving from 0 to -2. That's reduction is reducing. So we have other examples here also. Then we also have an example of a combustion reaction, and you can see how the oxidation numbers have been either increased or decreased. Hydrogenation is another reaction. So hydrogen is a good reducing agent. We said in our previous slide that oxygen is a good oxidizing agent. In this case, we are looking at hydrogen as a reducing agent. So you can see that hydrogen, when it reacts with phosphorus, phosphorus is being reduced from 0 to -3. So that's why they are referred to as good reducing agent. And you can see that hydrogen is moving from 0 to 1. That's increasing. Okay. So you can also see when hydrogen combined with metal, what happens? Sodium moves from 0 to +1. That is oxidation. While hydrogen moves from 0 to -1. That is reduction. So you can see for the rest how it reacts also with silver oxide. Silver is initially silver is +1 and it reduces to 0, and then from oxygen is -2 and then increases. Oxygen remains the same, as a matter of fact, for this reaction, -2 -2. But if you check hydrogen, you can see that hydrogen increases from 0 to +1. So you can see how this kind of reaction is affecting the oxidation state of each element that are involved. It's reaction of metals. So how did they react, and why are we really treating them separately and very importantly? So acid reacting with metals. So in a special case of more general phenomena, the things that we see around us, we can see around us some metals that are turning brown. They are moving from ion 2 to ion 3. So, and this kind of reaction is what we call single replacement reaction. So a reaction where one element replaces another is called single replacement reaction. So you can see A is reacting plus BC, and then A is displacing B. So to give you AC plus B. So metal A can replace metal B. Metal A has to be more reactive, or a non-metal A can replace non-metal C. That is, if A is more reactive than C. So redox reaction of metal. Let's consider this example. You can see that zinc is reacting with copper sulfate. All right, so from left, we start from left. This is the zinc, and we have the solution of copper sulfate here. So when you dip zinc into copper, you can see what happened. Copper is now reduced to copper 2 is now reduced to copper 1. Then zinc is now oxidized to zinc 2 plus. So by the time you finish the reaction, you can see that copper plated out on zinc bar. You can see the copper being plated out on the zinc bar. So this is an example of oxidation reduction that we're talking about. So you can see that copper is being reduced while zinc is being oxidized. What do we observe? You observe that the zinc ion take place of copper 2 plus ion in the solution. So copper atoms take place of zinc atoms in solid. Then we also observe that copper oxidizes zinc to zinc 0 to zinc 2 plus. Zinc 0 also reduces copper 2 plus to copper, just ordinary copper. So more active zinc replaces less active copper 2 plus. So zinc is easier to oxidize, and the reason why zinc is easier to oxidize, we'll see it on the table. So let's look at redox reaction of the metals. From what we've explained earlier, we said that zinc is being oxidized. So zinc is moving from ordinary zinc to zinc 2 plus. That's oxidation. So for reduction, copper is moving from copper 2 plus to copper. So that is reduction. So the number of electron transfer is equal. As you can see, zinc is losing 2 here, while copper is gaining the 2 electron. So the overall reaction is going to be, you have your zinc in its elemental state, combining with copper 2 plus to give us zinc 2 plus and copper. So in this case, you can see that zinc is moving from 0 to zinc 2 plus, that's oxidation, and copper is moving from 2 plus to 0, that is reduction. So redox reaction of metals. So when you consider the reaction of copper with zinc 2 plus, you can see that copper is less active and it cannot replace zinc 2 plus. So, but it can't replace zinc 2 plus. That means that it cannot reduce zinc 2 plus. So when you react copper 0 plus copper zinc 2 plus together, no reaction is going to take place. And there is a reason why no reaction will take place. So generally, the element that is more easily oxidized will displace one that is less easily oxidized from its compound. So elements higher in the activity series can displace elements lower in the activity series. Okay, so from this table, from what you said in the previous slide, you see that zinc is easily oxidized compared to metal. When you see the arrow is going down, it's increasing. So zinc is likely to be oxidized, but copper is less when you compare it to zinc. And that is why copper cannot displace zinc in the reaction. So consider the following example. You can see that magnesium is reacting with zinc chloride. All right, let's consider this example. We have magnesium reacting with zinc chloride. So we need to ask ourselves some questions. So we have to determine if the reaction will take place. Can it be classified as a redox reaction? If yes, we are to write and balance the half reaction taking place, followed by the overall reaction. So for example, does the reaction take place? The answer is yes. Is it a redox reaction? The answer is also yes, because magnesium, if you go and check the table that I showed you earlier, you can see that magnesium is higher than zinc when it comes to how easily oxidized. Okay. Yeah, so you can see that magnesium on the table, magnesium is higher than zinc, and that's why the reaction can take place. If magnesium is less on the table, then it's not going to take place. So we can see that, is this a redox reaction? We can say yes, because you can see that magnesium is moving from 0 to +2. Okay, so if you find the oxidation number of magnesium in this compound, you see that it's +2. Then for zinc is moving from +2 to 0, so that's reduction. So this is oxidation and that is a reduction. So if you want to write the oxidation reduction reaction, then you have Mg reacting with zinc 2 plus to give you Mg2 plus plus zinc. So let's talk about replacement reaction. Replacement reaction is the more electronegative element displaces the less electronegative element. So they're going to act as an oxidizing agent. So that's why you see chlorine is going to displace iodide ion here. So because chlorine is higher than iodine in the electronegativity series, that's why chlorine can easily displace iodine from Ki. So that's why you can see chlorine is from 0 to -1, and then iodine is moving from -1 to 0. That is oxidation, and this chlorine is being reduced. So you can see this is going to be the general reaction. Chlorine is moving from 0 to -1, and iodide ion is moving from -1 to 0. So learning check. So you have to predict if the following reaction will take place. Explain your answer. So when you have copper reacting with magnesium sulfate, so explain if it's going to take place. Okay. Then the second learning check. So you have iodine reacting with KCl. Can the reaction take place? So we move to half reaction. We've been writing the half reaction, but we're going to dwell more on it right now. So an half reaction is simply one which shows either reduction or oxidation, but not both. So you're not going to write them together. So you write reduction separately, and then you write oxidation separately. So for example, you have silver ion reacting with copper. Then you have silver and copper 2 plus. So from here, silver is moving from +1 to 0. Is that oxidation or reduction? That is reduction. We also have copper moving from 0 to +2. That is oxidation. So when you want to write, you write them separately. So you need to be able to look at redox reaction and separate out the two halves reaction in it. To do that, identify the atoms which get reduced and which one gets oxidized. So here are two half reaction from the example. So we have silver, like I said, silver ion is moving to silver, while copper is moving to copper ion, copper 2 ion. All right, so silver is being reduced because it's moving from +1 to 0. Copper is oxidized because it's moving from 0 to +2. So when you look at the two halves, you see that they are already balanced for atoms, which with one silver on each side and one copper on each side. So all we need to do now is to balance the charge. So to do that, add electrons to the more positive side. So you had enough to make the total charge on each side equal. So you must make sure that they are equal. So how do you balance this reaction, the silver one? You see, there is a positive here and there is 0 here. So how do you make this side equals to this side? How do you make it 0 generally? So that means you're going to add one electron. So by the time you have had one electron plus the negative plus positive, that's going to give you, cancel them each other out and gives you 0. The same thing here, this copper is 0 here, but we have copper 2 plus here. So that means you're going to add 2 electrons so that it's going to cancel the 2 electrons on the copper out. So balance this half reaction. You can see the first reaction is chlorine so you need to balance chlorine first. Then after balancing chlorine, then you need to balance the charges on them. So This is it. So we balance the chlorine first. There's 2 chlorine here, so you have to make it 2 here also. So here we have 2 negative charge here. So that means for us to balance it out, we must also add 2 electrons here, so that you have 2 electrons, then you have 2 electrons on the other side. Again, we have Sn moving to Sn2 plus. So Sn2 positive here. So that means that we're going to add 2 electrons so that they can cancel each other out. Then the last one is ion is moving from ion 2 to ion 3. So we have more of positive. Remember, you are going to add electrons to the more positively side. So this is the more positive side, and that's why we're adding 1 electron. So by the time you add 1 electron here, then you're going to have 2 plus 2 here, and the charge is also going to be plus 2. So try this learning check. So balancing half reactions in acid medium. So let's use some examples to look at how we can balance half reaction. So consider the following. We have manganese oxide is moving from manganese oxide ion is moving to just manganese 2 plus. So how do you balance this kind of equation? So balancing half reaction. So there are 3 other chemical species available in acidic solution. So you have water, you have proton, and you have electron. So water is present because the reaction takes place in water. Hydrogen is available because it is an acid solution. The electrons are available because we have transfer of electrons, and that's where they are redox reaction. So all these 3 must be used in getting your final answer: the water, the proton, and the electron. So let's see the example that we're talking about. So when you want to balance, you already see that we have 1 manganese on each side of the arrow. So that step is already done. That means manganese is balanced. Okay, so now oxygen is not balanced. So how do you balance oxygen? You do this by adding water. So add as many as needed to the side that needs oxygen. Which side needs oxygen? It is the product side. The right side needs oxygen. So how many oxygen do they need? They need 4 because we are having 4 here. So you're going to add 4 water molecules to that side. So in our case, the left side has 4 oxygen, while the right side has none. So you're going to add 4 water there to make it 4 oxygen. So you can see the manganese is balanced, the oxygen now is balanced. Now let's move to the next step. So we now need to balance the hydrogen that is present. So how many hydrogen do we have here? We now have 4. So the rule says that you add hydrogen ion as many as needed to the side that needs hydrogen. Which side needs hydrogen? This side needs hydrogen. And how many hydrogen? It's going to be 8 because we're having 8 hydrogen here. So that's why we have 8 proton added to the side. So as you can see now, all the elements are balanced. Now we are left with the charge. So this is be done using electrons. So when you want to balance the charge, you use electrons. So now, which of this side needs more electrons? If you look at this side, we are having 2 plus. If you look at this side, where if you had 8 plus minus 1, it's going to give you 7. So you are having 7 positive charge here because it's 8 plus minus 1. So it's going to give you 7. So that means we need 5 electrons on this side. So that by the time you subtract 5 from 7, it's going to give you 2. So that's why we are adding 5 electrons. So if you see 5 electrons there is also one electron there, making 6. So that is going to be 8 minus 6. So it's going to give you 2 plus. And then from there, you can now see that the charge is balanced because we're having 2 plus here already. So here is a second example that you can also look at. We can quickly look at this. So we can see that first thing is, let's check if chromium is balanced. So chromium is not balanced because we're having 2 chromium in and we are having 1 here. So you balance the chromium. So you put 2. So the chromium is balanced. Now the next step is, which side needs oxygen? The side that needs oxygen is this side. And how many oxygen do they need? This side needs 7 oxygen. And that's why we are adding 7 water there. So when we had 7 water. So the next step is, which side needs hydrogen? It is this side that needs hydrogen. So what do? You add more hydrogen to that side. So you add as many hydrogen as is needed. And how many hydrogen is needed? 7 times 2, which is 14. So that means 14 hydrogen is needed on this side. And that's why we add 14 H plus. Now, let's check the charges. The charge on this side is 2 times 3, which is 6 plus 6. How many do we have here? We're having 14, then we're having 2 minus here. So 2 minus plus 14 is going to give you plus 12. So that means how many electrons are we going to add here so that to balance with 6? So that means we're going to add 6 electrons. So by the time you add 6 electrons and you look at it very well, you see that you're having 6 electrons, minus 6 plus 14 and minus 2. So if you add them together, it's going to give you 6. So now everything is balanced, the charge and the elements in the reaction are balanced. So I believe this is a simple step, you just need to follow and practice. So you have more examples that you can do and study again. Then you have the learning check. We move to balancing half reaction in basic medium. Now, basic medium is a little bit different from the acid medium. And what do? So there are 3 other chemical species also available. They are water, they are OH minus, and we have electrons. So water is present because the reaction also takes place in water. Hydroxide ion is present because it's basic. You see, it's basic. For the acid medium, we were talking about hydrogen plus. Okay, so electrons is also available because it's a redox reaction. This is a typical example of the basic medium that we're talking about. So the same rules follow. We're going to say, okay, you balance the atom being reduced, oxidized, then you balance using oxygen, using water, you balance hydrogen using H plus, then you also balance the charge. So if you consider the example given above, you see that lead, it's balanced, so we leave it. So which side need oxygen? This side needs oxygen because there are 2 oxygen here. So that means we're going to add water molecule here. So you only had 1 because we only need 1 oxygen. So now we have 2 oxygens, we have 2 oxygens, it's balanced. So which side need hydrogen? This side needs hydrogen because we're having 2 hydrogen here. And that's why we had 2 H plus here, so that the hydrogen will be balanced. Then we now need to balance the charge. This side is more positively charged, and that's why we're going to add 2 electrons there so that the electrons can balance and the protons out. So that's why we're having 2 electrons, and then you can see that everything is balanced. So there is a final step that you need to do in when you're talking about basic medium, because it's basic. So that means you need to convert all the protons to water. So that means you convert the proton that were added. So instead of 2 H plus, you now put 2 water there because it's basic. So do this by adding OH ions to both sides. The side with H plus will determine how many hydroxide to be added, right? So this is the side with the H plus. How many H plus do we have? We have 2 H plus in the previous slide. So by the time you had 2 OH to this side, the OH, they are going to react with the hydrogen there to form water. That's why we're having water here. And this side is going to have 2 OH there. So in our case, the left side has 2 hydrogen, while the right side has none. And that's why we're having the 2 hydrogen here. We had OH minus. We had 2 OH minus to it. So when you have 2 hydrogens plus 2 OH minus, the two of them are going to come together to form 2 water. Okay, and that's why we're having that. So notice that when 2 hydroxide ion on the left were added, they immediately react to form hydrogen ion present. So they immediately react with, so this is the reaction when they I think I've mentioned this in the previous slide, that the two of them are going to come together to form water. So step 6, you now have to remove the duplicate molecules or ions. As you can see in our example, there are 2 water molecules on the left and there is 1 on the right. So if you go back to the previous slide, you can see that we're having 2 water here and then we're having 1 water here. So we want to remove the duplicates. So you cut out 1 here, then you leave the remaining water there. So the half cell reaction is now correctly balanced. If you look at it, you see that everything is now balanced. So you can also do this in a basic medium. This is another example. So first is to check if the element is balanced, and as you can see, manganese is balanced. So the next step is which side needs oxygen, and this is the side that needs oxygen. That's why you're going to add 2 water there. So by the time you add 2 water there, the next thing is which side needs hydrogen. Then you're going to add hydrogen there. How many hydrogen? This is 4 hydrogen. So you're going to add 4 hydrogen there. So when you add them together, then you look at the charge. So as you can see, this side is more, has more positive charges. And how many? It's 3. That's 4. And this is -1, so it's 3. So how many electrons do you need to add? You need to add 3. So that by the time you add 3, it's going to be 0, and it's going to be 0. There's no charges, 0. So the charge is also going to be 0 by the time you add 3 there. Now, the next step is to convert these 4 hydrogen to water. Is to convert them to water. So how do you do that? You're going to add 4 OH minus to each side. So by the time you add the OH minus to this side, this is going to be 4 water, because the OH are going to react with the hydrogen to give you water. But this one is going to remain there. So after that, look for the duplicate molecules or ions. And we are having 4 water molecules here, and we're having 2 here. So what happened? You're going to cross this one out, and then you're going to cross 2 out of here. So you're going to have 2 left, 2 water molecules left, but 0 water molecule left here, because they are duplicates. So by the time you now check this, then you see that the equation is now balanced. So try this learning check. So I think we'll probably try it together. So we want to balance this. First, let's write out the oxidation and the reduction side. So as you can see that ion 2 is moving from ion 2 to ion 3, that's oxidation. Then we have chromate is moving from +6 to +3, and that is reduction. So when you separate the 2 reactions and you have your oxidation and the reduction reaction, then you can move forward to balancing each reaction separately. So for example, you can decide to balance the oxidation reaction by adding electrons to read because the only thing that's not balanced is the electrons. So for this example, we're going to balance with 6 electrons. We're going to, the coefficient, we're going to increase it to 6. And if you see, this is 6 times 2, which is 12. And then we have 6 times 3, which is 18. So by the time you subtract 6 minus 6, then it's going to give you 12. So everything is balanced. So the reason why we use 6, we're going to get to it later in the example. So that is oxidation. Now, for reduction reaction, we're having oxygen present. So that means we need to balance oxygen. So we need to balance hydrogen as well by the time we balance the oxygen. So you add water to the right side because right side needs oxygen, and the chromium side needs oxygen. And then you add hydrogen to the left side to balance the water. So how many water molecules are you going to add? You're going to add 7 because we need 7 oxygen. So you add 7 to it. So that means that we're going to have 14 hydrogen. So that means that we're going to add 14 hydrogen to the left side. And that's why we're having 14. So by the time you add all those, you discover that you now have 12 positive charge, and we have 6 here. So how do you make their charges the same? So that's why we're adding 6 electrons to this side, so that by the time you add all the charges, they're going to be the same, and then you're going to have 6 positive here, then you're going to have 6 positive charge here on the other side. All right, so after that, you had both sides the same number of OH as H plus. So that means we want to eliminate remember this is basic medium, so we want to eliminate the protons here. So that means we're going to add 14 OH. So by the time you have 14 OH, this is going to be water. This is going to turn to 14 water. Then we're going to have 14 OH on that side. So at the end, you're going to have chromate plus the 14 water, then 6 electrons, and then we have this. So we are having duplicates, and this is the duplicate. We're having 7 water, then we have 14 water. So we can just take them out. So by the time we take them out, we'll be left with 7 water on this side. So now we have our oxidation reaction. Remember that we did in 2 slides before now. Then we have our reduction reaction there. So we can now say, okay, overall, if we want to write them together. Now, this is why I said we should use 6 coefficient the other time, so that now we can, if we equate the 2 of them together, then we can cross out 6 electrons. We call cross out 6 electrons for here, so that we have the left side, we're gonna write them together. Then we have the right side, we write them together. So we're gonna have 6 Fa3 plus 2 Cr3 plus, then we have plus 14 OH. So that is it. Let's do this learning check quickly. So you can see that perchlorate is moving from +5 to +4, and that is reduction. Then you can see chlorine moving from -1 to 0, and that is oxidation. That is increasing in oxidation number. So we're going to balance each reaction separately. Then we do the final equation. We combine them together. So first is to balance. So let's do the oxidation first. So we need to balance the chlorine, so that we put 2 here, then we have 2 chlorine here. So then you see that the charge, we're having 2 minus here, but we don't have anything here. So that's why we're adding 2 minuses, so that the charge can be balanced. So for reduction reaction, we are having oxygen. So we need to balance oxygen, then we need to balance hydrogen. So how do we balance oxygen? By adding water. How many water do we need? On this side, we're needing one oxygen to balance, because this is 2 oxygen and this is 3. So that's why we're adding 1 water there. So at the end, we're going to need 2 hydrogen to balance this side. So that's why we're adding 2 hydrogen. Then by the time you finish everything there, you discover that you need to add 2 electrons here so that the charges will be 0, because we're having 0 charge here. And that's where now we now have our reduction equation. So overall now, so we're going to have, we consider the reactant side, we're having 2 chlorine, then we have the perchlorate, then we have 2 hydrogen, then we also have 2 electrons, but the 2 of them will now cancel each other out. The 2 electrons that we have in oxidation is going to cancel the 2 electrons that we have in reduction. Then we have our chlorine, we have our chlorate, then we have the water molecule. That is it.